When the skin of a pressurized aircraft sustains structural damage, the Boeing Structural Repair Manual specifies a defined process for restoration. The damaged section of skin is to be cut out. A reinforcing plate, called a doubler, is then installed over the trimmed area. The doubler must extend at least 2 to 3 rows of fasteners beyond the boundary of the original damage into undamaged material. This geometry is not arbitrary. It creates an alternate load path that distributes stress evenly across the repair, preventing any single point from bearing a disproportionate share of the structural load. When installed correctly, the doubler restores the fuselage to its original design strength. It is the standard method for maintaining the pressure vessel integrity of an aircraft that may fly for decades under tens of thousands of pressurization cycles. Each cycle, from takeoff to landing, inflates and deflates the fuselage like a balloon. The skin must hold. The repair must hold with it. In May of 1980, a doubler plate was installed on the aft lower fuselage of a Boeing 747. The damaged skin beneath it was not cut out. The scratches from the original damage were not removed. The doubler was too small to cover the full extent of the damaged area. Scratches remained at the edge of, and outside, the outermost row of fasteners. The repair was recorded in the aircraft's maintenance logbook as having been completed in accordance with Boeing standards. It had not been. 22 years later, the aircraft carrying that repair broke apart in flight at 35,000 feet. 225 people were killed. The doubler had been installed to strengthen the structure. Instead, it concealed the damage that would eventually destroy it. The aircraft was a Boeing 747-209B. Registration B-18255. It was delivered new to China Airlines in 1979 and spent its entire operational life with the carrier. It was powered by 4 Pratt & Whitney JT9D7AW engines. By the time of the accident, it had accumulated approximately 64,800 flight hours and more than 21,300 flight cycles. It was the last remaining Boeing 747-200 in passenger configuration in the China Airlines fleet. The other aircraft of the same type had been converted to freighters or retired. B-18255 had, in fact, already been sold. China Airlines had agreed to transfer the aircraft to Orient Thai Airlines for $1.5 million. The accident flight was one of its final scheduled services for the carrier. After completing the round trip from Taipei to Hong Kong, B-18255 was to be handed over to its new operator. It never returned. On February 7, 1980, less than a year after delivery, B-18255 was operating as China Airlines Flight 009A service from Stockholm to Taipei, with stops in Jeddah and Hong Kong. During landing at Hong Kong's Kai Tak Airport, the aircraft was rotated to an excessively high attitude after touchdown. The aft lower fuselage struck the runway. The impact scraped and abraded a section of the fuselage skin between body stations 2080 and 2160, and a second section between body stations 2578 and 2658. The aft drain mast was torn off. The left outflow valve door was found partially open. This was a tail strike. It is not uncommon. It is not inherently catastrophic, but the damage it leaves behind must be repaired correctly. The aircraft was ferried back to Taiwan the same day, unpressurized. A temporary repair was completed overnight. 2 reinforcing doublers made of 0.063-inch 7075-T6 aluminum alloy were installed over the abraded skin, and the aircraft was returned to revenue service. The temporary repair instructions explicitly did not require the damaged skin to be removed before the doublers were applied. That step was reserved for the permanent repair, which was to be completed within 4 months. The repair held did. The skin beneath it did not. From May 23rd to May 26th of 1980, a China Airlines maintenance team carried out what was recorded as the permanent repair. The aircraft logbook documented the completion date as May 25th, 1980. However, the configuration of this repair, as determined decades later from the physical evidence recovered after the accident, did not comply with the Boeing Structural Repair Manual. The SRM provided 2 acceptable repair methods. The first was to replace the entire affected skin panel. The second was to cut out the damaged section and install a doubler that extended well beyond the boundaries of the damage. China Airlines followed neither. Evidence recovered from the wreckage showed that the maintenance team had attempted to sand or blend the scratches but had not removed them. A doubler was then installed directly over the damaged skin. The doubler was too small. It did not extend sufficiently beyond the full area of damage. Critically, skin scratches from the original tail strike remained at and outside the outermost row of fasteners securing the doubler. At the time of the repair, China Airlines classified the work as minor, which under the airline's procedures required minimal documentation and minimal supervisory approval. A detailed contemporaneous description of the permanent repairs configuration does not exist. The configuration was reconstructed after the accident, not from maintenance records, but from the wreckage itself. The record stated the repair was compliant. The metal told a different story. What followed was a process that took 22 years to complete. It was governed by physics, not by chance. It began with the scratches. The tail strike had left longitudinal scratches running fore and aft along the fuselage skin, perpendicular to the hoop stress direction. This orientation matters. Hoop stress is the circumferential tensile load that the fuselage skin bears during every pressurization cycle. When the cabin is pressurized at altitude, the fuselage expands outward. When it depressurizes on the ground, it contracts. This cycle repeats with every flight. Over 21,000 flights, the fuselage of B-18255 inflated and deflated more than 21,000 times. A scratch on the surface of the skin acts as a stress concentrator. At the base of each scratch, local fatigue stress is elevated above the surrounding material. This elevated stress shortens the fatigue life of the metal at that point and accelerates the initiation of cracks. The scratches on B-18255 were not in a random location. They were positioned just outside the outermost row of fasteners securing the doubler. This meant they were in a zone where the load transition between the reinforced area under the doubler and the unreinforced skin created the highest stress gradients. It was the worst possible location for unrepaired damage. Over time, small fatigue cracks began to form at multiple scratch locations. This is a condition known as multiple site damage, or MSD. Each individual crack was microscopic at first. Each one grew with every pressurization cycle. The growth rate was measured in microns. Scanning electron microscopy performed during the investigation found fatigue striations spaced approximately 2 microns apart near rivet locations. 2 microns per cycle, invisible to the naked eye, but cumulative, over thousands of cycles. Invisible becomes measurable, measurable becomes structural, structural becomes catastrophic. As the cracks propagated, they grew from the outer surface of the skin inward, through the thickness of the metal. Then they began to extend along the length of the fuselage. Because the scratches were positioned just under the lip of the doubler, the growing cracks eventually impinged on the underside of the doubler plate. This created a phenomenon called fretting, a mechanical rubbing between two surfaces in contact under load. Each pressurization cycle caused the cracked skin to flex against the doubler. The doubler, rigid and firmly fastened, resisted this movement. The result was a pattern of hoop-wise fretting marks on the inner surface of the doubler, marks that the investigators would later use to confirm that the crack had been moving beneath the plate for thousands of cycles. The doubler created an additional problem. Under normal circumstances, when a fatigue crack in a fuselage skin reaches sufficient length, the skin bulges outward under pressurization. This bulging is visible during walk-around inspections. It is one of the primary visual indicators that a crack exists, but the doubler physically restrained the skin from bulging. The damage remained flat. The external surface of the aircraft showed no visible deformation. The repair that was supposed to strengthen the structure was actively preventing the detection of its own failure. The small MSD cracks continued to grow and began to link. When adjacent cracks propagate far enough, they coalesce into a single continuous crack. The investigation later confirmed a main fatigue crack of 15.1 inches in through thickness length, along with multiple smaller fatigue cracks in the same region. Residual strength analysis conducted after the accident indicated that the combination of the main crack and the surrounding MSD was sufficient to produce a continuous crack within a two-bay structural region of approximately 40 inches. Further analysis determined that the fuselage's residual strength would be compromised by a continuous crack of 58 inches or longer under normal operational loads. The investigators could not determine the exact length of the crack before the accident flight. But the extent of fretting marks on the doubler and the deformed cladding found on the fracture surfaces led the Aviation Safety Council to conclude that a continuous crack of at least 71 inches, nearly 6 feet, was present before the in-flight breakup occurred. 71 inches exceeds the 58-inch threshold by a significant margin. The structure was operating beyond the limits of its design tolerance. The only question was when, not whether, it would fail. There was evidence that the crack had been signaling its presence. China Airlines permitted smoking on board its flights until 1995. For years, cigarette and cigar smoke filled the pressurized cabin. Pressurized air, carrying suspended particulates from the smoke, was continuously pressing against the interior surface of the fuselage skin. Where the skin was intact, this pressure was contained. Where the skin was cracked, the pressurized air leaked through. On the exterior of the aircraft, around the repair doubler, at approximately body station, 2,100 brown nicotine stains had accumulated over time. These stains were the residue of cabin air escaping through the fractured skin. Staining around a pressure vessel repair is a recognized indicator of a possible breach. It means the seal between the interior and exterior has been compromised. In November 2001, during a maintenance inspection associated with the Repair Assessment Program, photographs of the repair doublers on B-18255 were taken. The photographs showed visible traces of staining on the aft lower lobe fuselage around the area of the 1980 repair. The stains were documented. They were not investigated. The crack had been speaking. No one was listening. 6 months later, the aircraft disintegrated in flight. The investigation also revealed that mandatory inspection schedules had not been followed. The first corrosion prevention and control program inspection of B-18255 was conducted in November 1993. The second was due in November 1997. Reduced aircraft utilization led to the postponement of flight hour-based inspections, and the corresponding CPCP dates were passed without completion. From November 1997 onward, the aircraft had 29 CPCP inspection items that had not been accomplished in accordance with the China Airlines Maintenance Program or the Boeing 747 Aging Airplane Corrosion Prevention and Control Program. The airline's oversight and surveillance systems did not detect the missed inspections. The Civil Aeronautics Administration of the Republic of China, the regulatory authority, did not identify the scheduling deficiencies during its audits. The last internal inspection of the area near the 1980 repair had been conducted approximately 4 years before the accident. The FAA noted that it was unclear whether the crack would have been noticeable by visual inspection methods, since the crack had grown inward from the outboard side of the skin, a direction that made detection through standard internal visual inspection uncertain. This was not the first time a Boeing 747 had been destroyed by a faulty tail strike repair. The precedent existed. It had killed 520 people. On August 12, 1985, Japan Airlines Flight 123 crashed after its vertical stabilizer separated in flight. The cause was an improperly repaired rear pressure bulkhead, damaged in a tail strike in 1978. A doubler plate had been installed that did not conform to Boeing specifications. Over 7 years of pressurization cycles, the bulkhead failed. 520 of the 524 people on board were killed. The failure mode was the same in principle: a tail strike, an improper repair, a doubler that did not meet the manufacturer's standards. Progressive structural degradation, catastrophic failure. JAL 123 had established this sequence 17 years before Flight 611. The industry knew. Aging aircraft programs were initiated. Inspections were mandated, but the specific vulnerability that Flight 611 would expose, a non-compliant repair hiding damage beneath a doubler on an individual aircraft, was not the subject of a systematic fleet-wide review. The repair on B-18255 had been performed in 1980 before JAL-123 occurred. After JAL-123, the industry had reason to look back. It did not look at B-18255. On May 25, 2002, a Saturday afternoon, China Airlines Flight 611 departed Chiang Kai-shek International Airport in Taipei, bound for Hong Kong International Airport. The route was one of the most heavily traveled air corridors in the world. The aircraft had not been the originally scheduled equipment. A Boeing 747-400 had been planned for the flight, but was reassigned. B-18255, the aging 747-200, on the verge of transfer to Orient Thai Airlines, was substituted. On board were 206 passengers and 19 crew members. 114 of the passengers were members of a group tour organized by several travel agencies. The flight crew consisted of Captain Yi Ching Fong, 51 years old, with approximately 10,100 total flight hours. First Officer Xie Ya Xiong, 52, had approximately the same level of experience. Flight Engineer Chao Sen Kuo, 54, had logged more than 19,000 hours. All three had rested for more than 24 hours before the flight. The captain had been called to duty from standby. There was nothing in the crew's condition, qualifications, or operational environment that suggested anything other than a routine flight. The aircraft took off from runway 06 at approximately 15:08 local time. The takeoff roll and initial climb were normal. The crew completed standard procedures. Flaps were retracted in sequence. The autopilot was engaged. Air traffic control cleared the flight direct to the Chali waypoint with instructions to resume own navigation. At 15:16, Taipei Area Control Center cleared Flight 611 to climb to flight level 350, 35,000 feet. The climb continued without incident. The cockpit voice recorder captured routine conversation. The first officer broadcast to the cabin crew that in-flight service could begin. The flight engineer relayed an operational report. There were no warnings, no alerts, no system anomalies. For approximately 20 minutes after takeoff, Flight 611 was indistinguishable from any other departure on the Taipei to Hong Kong route. The flight data recorder captured normal engine performance, normal control surface positions, and a standard climb profile throughout. The last recorded crew verbalization on the cockpit voice recorder occurred at approximately 15:26. The flight data recorder continued to record normal parameters until approximately 15:28, at which point the data ceased. Seconds later, the aircraft disappeared from radar. There was no distress call, no transponder signal change, no communication of any kind from the flight crew. The aircraft simply vanished from the system at 35,000 feet. At 17:05, a military C-130 aircraft spotted wreckage floating on the surface of the Taiwan Strait, approximately 23 nautical miles northeast of Mekong in the Penghu Islands. The first body was recovered at 18:10. The breakup occurred at or near the aircraft's intended cruising altitude. Radar data indicated that the aircraft separated into multiple segments. Debris was scattered across a wide area of the Taiwan Strait. Items from inside the aircraft, including magazines, documents, luggage, photographs, currency, and a blood-stained China Airlines pillowcase, were found as far as 80 miles from the crash site, in villages in central Taiwan. This distribution was consistent with a high-altitude in-flight disintegration in which debris was carried by upper-level winds. All 225 people on board were killed. Of the 225, remains of 175 were recovered and identified. The first 82 bodies were found floating on the ocean surface and retrieved by fishing boats and military vessels. No signs of burns, explosives, or gunshot wounds were found on any of the recovered remains. The injury patterns were consistent with high-altitude decompression and high-velocity water impact. The investigation was led by the Aviation Safety Council of Taiwan, with technical assistance from the United States National Transportation Safety Board, Boeing, the Federal Aviation Administration, and Pratt and Whitney. The investigation would take nearly 3 years to complete, making it one of the longest aviation investigations in Taiwanese history. The cockpit voice recorder and flight data recorder were both recovered from the seabed. The flight data recorder's Lockheed 209F unit was retrieved on June 19, 2002, nearly a month after the accident. Its case was fractured and the tape was water damaged, but it was immediately submerged in fresh water to halt corrosion. The data was fully usable, covering 32 minutes of flight up to the moment of breakup. The cockpit voice recorder provided 31 minutes and 51 seconds of good quality audio. Neither recorder revealed any indication of an anomaly before the breakup. This absence of warning was itself significant. It eliminated scenarios involving gradual system degradation, engine failure, or crew incapacitation. Whatever destroyed the aircraft did so without providing any advance indication onto the instruments or the crew. The investigation initially considered multiple possible causes, including a fuel tank explosion similar to TWA Flight 800, a bomb or explosive device, structural corrosion, and metal fatigue. No evidence of explosion, fire, or criminal act was found on any recovered wreckage or remains. The determination of the breakup origin relied on wreckage distribution analysis, a technique also used in the TWA 800 investigation. The principle is straightforward in a high-altitude breakup. The pieces that separate first travel the farthest from the main debris field because they are released at the highest altitude and have the longest fall time, during which upper-level winds carry them laterally. By mapping the recovery locations of individual pieces and correlating them with their position on the aircraft, investigators can reconstruct the sequence of disintegration. For Flight 611, this analysis determined that the aft section of the fuselage had separated first. Items from inside the aircraft were found up to 80 miles away, in villages in central Taiwan. This directed the investigation toward the lower aft fuselage, specifically the area around Body Station 2100, the area of the 1980 tail strike repair. 22 years of flying, and the answer was where the damage had always been. The key physical evidence came from recovered sections of the aft fuselage skin near Body Station 2100 between stringers S48L and S49L. This was the location of the 1980 tail strike repair. Examination revealed flat fracture surfaces along the edge of the external repair doubler. Penetrant inspections and optical microscopy at up to 50 times magnification confirm multiple fatigue crack origins on the skin faying surface. Scanning electron microscopy of the fracture surfaces revealed fatigue striations with spacing of approximately 2 microns near rivet locations, consistent with slow, steady crack growth under cyclic loading. The main through-thickness fatigue crack measured 15.1 inches. Multiple smaller fatigue cracks were confirmed in the same region, all originated from the scratching damage left by the 1980 tail strike. The repair doubler showed fretting marks on its inner surface, the physical record of a crack that had been moving beneath the plate for thousands of flights. Each mark corresponded to a pressurization cycle, each cycle to a flight. The pattern was oriented in the hoop direction, consistent with the cyclic inflation and deflation of the fuselage during normal operations. The doubler had not stopped the crack. It had ridden on top of it, concealing it, for 22 years. Residual strength analysis confirmed that the combination of the main fatigue crack and the surrounding multiple site damage was of sufficient magnitude to produce a continuous crack capable of compromising the fuselage under normal operational loads. The threshold for structural failure was a continuous crack of 58 inches. The evidence suggested that at least 71 inches of continuous cracking was present before the breakup. The structure failed not because it was subjected to extraordinary loads, but because ordinary loads exceeded the residual capacity of a fuselage that had been weakening for 2 decades. The aircraft was within its normal flight envelope. The stresses it experienced during the climb to 35,000 feet were the same stresses it had experienced on every previous flight. On this flight, the structure could no longer bear them. The Aviation Safety Council published its final report on February 25, 2005. The report presented its conclusions as findings in 3 categories: findings related to probable causes, findings related to risks, and other relevant findings. There were 6 findings related to probable causes. The in-flight breakup was highly likely due to structural failure in the aft lower lobe section. The fatigue cracks had initiated from scratching damage associated with the 1980 tail strike. The repair had not been accomplished in accordance with the Boeing Structural Repair Manual, and the operator's maintenance inspections had not detected the ineffective repair or the cracks developing beneath the doubler. The report also identified 7 findings related to risks, including the missed CPCP inspections, the unaccomplished maintenance items, the failure of both China Airlines and the CAA to detect these emissions, and the staining visible in November 2001 photographs that indicated possible hidden damage. China Airlines disputed portions of the report, stating that investigators had not recovered the specific pieces that would prove its conclusions. The organizational analysis extended beyond the 1980 repair. China Airlines had classified the permanent repair as minor, requiring minimal documentation and approvals. This meant the repair received less scrutiny than it warranted. And once the records indicated compliance, every subsequent inspection began from that assumption. The repair was treated as a known quantity. It was not re-examined. It was not reopened. The doubler was there. The record said it was installed correctly. The system moved on. Nothing failed quickly. That was the problem. The airline's inspection programs, including those implemented after the 1988 Aloha Airlines Flight 243 accident, had conducted inspections in the vicinity of the repair area but had not detected the growing fatigue damage beneath the doubler. The detection architecture operated on 3 tiers, and the repair defeated all 3. Visual inspection relies on outward bulging of the skin. The doubler prevented bulging. Surface staining from pressure leakage is a secondary indicator. The staining was present but was not flagged. Non-destructive inspection using ultrasonic or eddy current techniques can detect subsurface cracking, but these were not applied to the 1980 repair area before the accident. The crack was architecturally hidden, not by intent, but by the interaction of a non-compliant repair, a concealing doubler, and an inspection system that trusted the records more than the metal. The reforms were directed at the systemic vulnerability that Flight 611 had exposed. The FAA issued airworthiness directives requiring inspections of all Boeing 747 pressure vessel repairs and mandating the incorporation of enhanced aging airplane maintenance programs with specific fatigue monitoring thresholds. Boeing issued a service bulletin specifying ultrasonic and eddy current non-destructive inspection protocols for tail strike-affected fuselage skins. The ASC issued 21 safety recommendations to China Airlines, the CAA, Boeing, the FAA, and other bodies. The central requirement was clear pressure vessel repairs that could be hiding damage must be identified and inspected using methods capable of detecting what visual inspection alone cannot. China Airlines phased out its remaining 747-200 fleet. The structural failure of China Airlines Flight 611 took 22 years to develop. It began with a tail strike. It progressed through a non-compliant repair that was documented as compliant. It was concealed by the very doubler meant to fix it. It was signaled by nicotine stains that were photographed and not investigated. It was missed by 29 unaccomplished inspection items. It was preceded by the destruction of Japan Airlines Flight 123, which had demonstrated the same failure mode 17 years earlier. No industry-wide review identified the defective repair on B18255. The central lesson of this accident is that a maintenance error, once concealed by a repair that appears compliant, can become invisible to every safeguard the system relies upon. Visual inspections cannot see beneath doublers. Maintenance records cannot detect what was falsely recorded. Non-destructive inspection techniques are effective, but only if applied to the right areas. On B-18255, they were not. The crack grew beneath the doubler at the rate of approximately 2 microns per pressurization cycle. For 21,398 cycles in the final months, the multiple site damage cracks linked into a continuous fracture estimated at more than 71 inches. The fuselage was compromised at 58 inches. By the time Flight 611 took off on May 25, 2002, the aircraft was structurally incapable of sustaining the loads it would encounter during a normal climb to cruising altitude. The crew had no indication of the condition. No system on the aircraft was designed to detect it. The aircraft's logbook recorded a compliant repair. The doubler plate, the reinforcement that was supposed to guarantee the integrity of the pressure vessel, was holding the two sides of a 6-foot crack in proximity while preventing anyone from seeing it. The aircraft was 22 years old. It was on one of its last flights. The repair that would destroy it had been performed on May 25, 1980. The accident occurred on May 25, 2002, 22 years to the day. The repair was logged as complete. The crack was not